Hi everyone. Let's finish up Beer's law by talking about some of the limitations. The first limitation is that Beer's law only works for monochromatic radiation, but to me that really isn't such a terrible limitation because in most of our experiments that's what we use. The next one is Beer's law does have a limit in terms of concentration. It only works for dilute solutions roughly less than 0.01 molar, but again, I think for most of our experiments it's not such a big deal. We've been working at the low parts per million range. And then here's the last limitation. You may have trouble if your analyte exists in more than one form. Now, what does that mean? You'll have to think back to maybe when we were talking about acids and bases and all the different forms in which they can exist. Let's talk about this last limitation in a little bit more detail. So what you're looking at here is a plot of absorbance versus concentration. I'm pretty sure the units were in ppm. This is from one of my former students, and not the best looking cal curve, is it? Look at that R squared value. But when you look more closely at this calibration curve, don't you kind of see a linear range here? And then perhaps another linear range here. So remembering Beer's law, and what have we done? We've plotted absorbance versus concentration. This is the slope of our line, isn't it? So now the question becomes, why did this slope change? And if you think about what the slope is, this is the slope. It's the molar absorptivity times B, the path length. Well, B wasn't changing in these experiments. It must be the molar absorptivity that had changed. And that's a hard question to answer. Let's back up a little bit and talk about a normal experiment where you have some solute X, let's call it, that only exists in one form. And what you're looking at here are standards containing 1, 2, 3, and 5, let's say parts per million of X. And when we make our calibration curve, and again, that'll be a plot of absorbance versus concentration. Here is the signal for R1. Here is the signal for R2 parts per million. There it is for 3. And there it is for 5. Look how beautiful. Everything is normal. We have a nice straight line because our solute exists in only one form. But what if X can be protonated? So here's an equilibrium to remind you. Now you have two forms in which X can exist, the unprotonated and the protonated form. So maybe the protonated form has some molar absorptivity, and maybe the unprotonated form has some molar absorptivity. And what if they're not equal? So at low concentrations, perhaps the major form is X, but at higher concentrations, you're going to get more and more of that protonated form. Look what happens at 3 ppm. And look what happens at 5 ppm. So now take it a step further. I asked you to imagine if the molar absorptivities of the protonated and the unprotonated forms were different, but now what if the molar absorptivity of the protonated form was less than the molar absorptivity of the unprotonated form? How does that change your calibration curve? Well, here we have, just as a reference, our everything is normal line. And if we were to plot this first standard that contained mainly the unprotonated form X, we would get a signal similar to what we got when everything was normal. But as we increase the concentration and we start seeing more and more of that protonated form, and if that protonated form has a lower molar absorptivity, isn't that going to make your absorbance lower? Yes. And look what happens at 3 ppm when you have even more of that unprotonated form with, again, the lower molar absorptivity. The absorbance is lower, and the same thing at 5. So this is an example of when Beer's law fails because the solute existed in two different forms. Now, you might also observe this not because this is happening, but there's always going to be a limit to the linear range of any calibration curve. But keep these limitations in mind of Beer's law. It's a good law. I hope you enjoyed it, and thanks for listening.